So today we're going to get into what is, no joke, one of the most profound and, honestly, kind of unsettling questions in all of science. It's a mystery that makes you question, everything you think is real. Let's just jump right in.
And hey, you don't have to take my word for it. The legendary Richard Feynman, he called the experiment we're about to discuss the only mystery of quantum mechanics. I mean, when a genius like Feynman says something is the one big mystery, you know you're dealing with something absolutely fundamental.
So what is this huge mystery? Well, it all comes down to a question that sounds super simple on the surface. Think of us as detectives for a minute. The big question is, what is the universe doing when nobody is looking? And trust me, the answer is way, way stranger than you could possibly imagine. Our investigation kicks off with probably the most famous and definitely the weirdest experiment in all of modern physics. People have been doing versions of this for more than 200 years, and it still blows our minds by showing us just how bizarre the rules of reality really are. Okay, so here it is, the whole paradox right here. On the left, you see what happens when we're not looking. We shoot something like an electron at two slits, and it acts like a wave. It goes through both slits at once and creates this cool interference pattern. But, and this is the crazy part, the instant we put a detector there to see which slit it goes through, bam, the wave behavior is gone. Look at the right. We just get two simple lines, like we were throwing tiny little balls. The bottom line, just by looking, we change what happens. The act of observation itself changes reality. And you might be thinking, okay, maybe that's just some weird thing that happens with light or tiny electrons. Nope. As you can see from this timeline, this bizarre wave-particle duality thing has been confirmed again and again. It started with light way back in 1801, then electrons in 1927, and by 1999, scientists were getting the same effect with these massive molecules they call buckyballs. So this isn't some niche little quirk. This weirdness is baked into the very fabric of our universe. Which brings us to the observer's dilemma. I mean, how? How does the simple act of looking at something fundamentally change what it does? This question right here is the absolute core of what physicists call the measurement problem. And there's a name for this magical moment when the mystery happens. It's called wave function collapse. Before we look, a particle is just, well, it's a wave of possibilities. It could be here, it could be there, it's kind of going through both slits at the same time. It's this fuzzy cloud of potential. But the moment we measure it, that whole cloud just collapses, instantly, into one single definite point in reality. This table really nails the difference between our normal, everyday world and the quantum world. Think about it. In our world, if I check the location of a bowling ball, I'm just finding out where it already is. The information was pre-existing. But down in the quantum realm, the measurement doesn't just reveal a property. It actually seems to create it. It's like the universe hasn't decided yet, and our act of looking forces its hand, making it choose one reality out of all the possibilities. So the big question is why? Why does this collapse even happen? This is where our detective story gets good, because we have a few different suspects. A few different theories, all trying to explain what's going on. Let's check out the main ones. Okay, so one of the early ideas, and it's a pretty wild one, was that consciousness is the secret sauce. The idea, pushed by big names like John von Neumann, was that the universe is just this blurry soup of possibilities, until a conscious mind, like you or me, looks at it, and our observation is what forces it to snap into a single concrete reality. It's a really cool philosophical idea, but it's also pretty tough to square with science. Now, the much more mainstream scientific view today is something called quantum decoherence. And what's great about this idea is that it gets rid of the need for some special conscious observer. It basically says that any interaction with the environment is enough to cause the collapse. A particle just bumping into a single air molecule or getting hit by a random photon of light. That's enough to make all that quantum weirdness leak out, forcing it to act like a normal classical particle. And this right here shows you exactly why most scientists are on board with decoherence. See, it's not some extra made-up rule they had to tack onto the math. It just falls out of the existing quantum theory naturally. And the real kicker? Look at that last row. Unlike the consciousness idea, decoherence is a physical thing that we can and have actually seen and measured in the lab. That's a huge deal. Just when you think this whole thing couldn't possibly get any weirder, it does. A new version of the experiment came along that's so mind-bending, it seems to mess with our fundamental ideas about time itself. This leads to an absolutely wild question at the core of an experiment called the delayed choice quantum eraser. And the question is this: can a choice you make now, in the future, affect something that has already happened in the past. The setup is basically, what if we let a particle go through the slits, make its pattern on the screen, and only after all that is done, we decide whether or not to look at which path it took. And the results are just staggering. Get this, as the table shows, if we decide, in the future, to keep the which path information, the pattern that already formed in the past looks like a particle pattern. But if we decide to erase that information, the pattern that's already there in the past seems to retroactively change into a wave pattern. It's baffling. Okay, hold on. Before you run off to build a time machine, here's the really important scientific fine print. The verdict is, no, this doesn't mean you can send messages to the past. This spooky wave pattern only shows up after we've collected all the data and sorted it in a very specific way. If you just look at the raw data, it's a meaningless blob. So, cause and effect is safe, for now. But it sure does suggest that our neat and tidy idea of the past might be a lot fuzzier than we're comfortable with. Now, all this quantum craziness has, you can imagine, fueled some even more radical ideas. And one of the most popular is the simulation hypothesis, which tries to connect all this weirdness to the video games and digital worlds we build ourselves. The core idea is actually a pretty neat analogy. Think about a video game. The computer doesn't render the entire massive game world in full detail all the time, right? That would take way too much processing power. It only renders the little bit that your character is actually looking at. Well, the simulation hypothesis says maybe the universe does the same thing. It saves on cosmic processing power by leaving everything in a fuzzy, low-res wave state and only renders the sharp, high-def particle reality when an observer actually looks at it. And proponents of this theory take it even further. They look at the fundamental constants of physics and say, hey, maybe these are just the technical specs of the simulation. So the speed of light, that's not some deep cosmic law. That's just the processor speed of the universe's computer. The Planck length, the smallest possible slice of space, that's just the pixel resolution of our reality. Quantum uncertainty? Just an optimization trick to save on calculations. But there's a really big scientific rebuttal to all this. Because when physicists try to actually simulate quantum physics on our best supercomputers, they find out it's not a shortcut at all. In fact, it's the complete opposite. It's ridiculously, impossibly complex. Just look at this number. To fully store the information and simulate the quantum state of just a few hundred electrons, you would need a classical computer built out of more atoms than we think exist in the entire observable universe. I mean, that number is just incomprehensible. So, whatever nature is doing, it's handling this insane complexity with no effort at all, while for us, even simulating a tiny piece of it is basically impossible. So where does that leave us? If it's not a conscious observer, and it's probably not a cosmic video game, then what's going on? Well, the most cutting-edge thinking on this doesn't really give us a simple, neat answer. Instead, it offers a totally profound way of rethinking the entire question. One of the coolest modern ideas is called relational quantum mechanics from physicist Carlo Rovelli. And it says we're asking the wrong question. We shouldn't ask, what is the electron really doing? We should ask, what is the electron doing in relation to the thing observing it? In this view, things don't have properties on their own in isolation. Properties like position or spin only exist in the moment of an interaction. So reality isn't a bunch of independent objects. It's a vast, interconnected network of relationships. And that really leaves us with this one final, powerful thought to chew on. Maybe the biggest takeaway from all of this is that our everyday view of the world, a world of solid, separate objects with definite properties, is just an illusion. It seems that reality isn't some fixed thing that we just passively look at. Instead, it's something that's, well, it's negotiated. It emerges from a whole sea of possibilities only when something or someone interacts with it. We don't just observe the universe. We are, in a very real sense, participants in creating it, moment by moment.